Hi guys, welcome to Lab 2, Motion of a Falling Object. My name is Zach McGill. We're going to start with a quick introduction. We'll be exploring the motion of a falling object, in this case a shoe, dropped from a known height. Then we'll model the data with both a tracker analyzed version and then two computer models. And we'll see why the models fail to predict the object's motion, as well as what the presence of drag force does to affect the motion. And then finally, we'll explore the idea of terminal velocity in relation to this object. So the object of study is a leather shoe of approximately 589 grams. And we have the model video in tracker that we can look at down here. The initial velocity of the shoe is 0.79 meters per second, and the final velocity of the shoe is 5.12 meters per second. As you can see, we use the center of mass of the shoe as the points, and this data was analyzed by tracker, and we can see a increase in the negative y direction velocity, which is what we were looking for. Moving on to the models we created using VPython. These models are all based on Newton's second law, which is V final equals V initial plus F net over mass times delta T. And in this case, we actually have F net in both models. In one, it's just the weight force, and the other, it's the weight force minus the drag force, which is different from the first lab. So we'll go ahead and look at the first model, which models the motion without a drag force. We would expect this model to overpredict the distance that the shoe would travel, but in fact ours underpredicts the distance the shoe travels, and we're going to look at in a slide or two why this happens. It's not normal, and the same thing occurs in the model with drag against the tracker data. It's slightly more accurate, but we would expect these to be very similar, and if anything, we would expect the model to overpredict the distance traveled. We'll answer the question of why don't these models accurately predict the shoe's motion. Here we're going to go ahead and look at the VPython data. And first we got to scroll back up here. So there's some important information we had to enter. So we have gravity here, which we've defined. We have a proportionality constant, which has a magnitude proportional to the velocity squared of the shoe, which is something we're going to use to calculate the drag force. Which then we have all our forces defined here, as well as Newton's second law written out in code again, so that we can track the object's position for every delta t. And then down here we have another new variable, which is arrow scale, which we use to create arrows that model, or I guess point in the direction of the forces acting on the shoe. And that value was found using a base of 2 meters and then dividing by the weight force. Here we've got both the model that's going to look similar to the tracker graph, and then this other view which shows us the weight force as this downward yellow arrow and the drag force as this small blue arrow. And you can get an idea of how much larger the weight force is than the drag force. Next, we're going to look at why the models aren't accurate in modeling the data. The problem lies with the actual experiment, not with the model or the physics. The shoe could be dropped with some initial force. The shoe may not be completely dropped in only the y direction. There may be some z movement. And then the most likely problem is perspective distortion, which occurs because our video is not filmed from a perfect angle, and it's kind of difficult to tell where exactly the shoe's falling in tracker. The gist is that these models actually show the actual motion better than the tracker video does. These models are based completely on physics, where the video has this distortion, which is causing inaccuracies. We're going to continue on to two questions relating to terminal velocity in relation to the model. The first question asks whether either of the models can predict a terminal velocity, and the answer is right now they cannot. Terminal velocity is where the downward weight force is equal to the upward drag force, and thus you have no acceleration. Neither of these models run for long enough to show us the terminal velocity. However, the second model with drag force could be run for a length of time that would show us a terminal velocity. We'd have to increase the time to, say, 100,000 seconds. And then we actually do that in the what if question, which asks if we threw the shoe downward, would it have an increased effect on the terminal velocity? And the answer is it won't. We ran the model at t is 100,000 seconds, and for both a 0 initial velocity and a 2 meter per second downward initial velocity, the terminal velocity was negative 2,9,300 thousand meters per second, which is very fast, and just means that the initial velocity does not have an effect on the terminal velocity. Thank you guys for watching this video, and I'll see you next time.